Irodov problem number 1.239. Calculate the moment of inertia of a copper uniform disk relative to the symmetry axis perpendicular to the plane of the disk if its thickness is equal to b and its radius is equal to r. And second is of a uniform solid cone relative to the symmetry axis if the mass of the cone is equal to small m and the radius of its base is equal to r. Okay, let's draw. So we have a disk, okay, its thickness is b, okay, and let's say the axis about its symmetry point goes like this, okay. This radius is given as capital R and this thickness of the disk is given as b. Okay, so we have to find the moment of inertia about this axis. Okay, so first up, we know the moment of inertia of a disk, of a flat disk, no thickness, about its axis if this is r, the mass of this disk is m, the moment of inertia is half m r square. So we will use this result to find the moment of inertia of this disk which has a certain thickness. Okay. So let's say we take a small element x of this thickness. So this is the disk. Let's say we take at a distance x, we take a small element dx. Okay. So the resultant disk that forms of this element dx can be thought of like a flat disk. So what is the moment of inertia of that small disk of thickness dx? Let's say that is di is half the mass of the small element dm times the radius of that small element is still r, so r square. Now we need to find out dm. Okay, we know density rho is mass by volume, right? So let's say this dm mass is dm, and what is the volume of this small element? Its surface area is pi r square and the thickness is dx, so times dx. So we can write dm is pi r square rho times dx. So we substitute this back here. So di is half dm is pi r square rho dx times r square, or we can write this as half pi r to the power 4 rho dx. Now to get the moment of inertia of this entire plate, we will integrate. So I will be integral. Now x is varying from what? From 0 to b, because the thickness is b. So 0 to b, half pi r to the power 4 rho dx. Now all of this is a constant. Integral dx is x. So this is equals to half pi r to the power 4 rho b. So that's our answer. Okay. Next is we have to find the moment of inertia of a solid cone about this axis. So it passing through the symmetry point. Okay. All right, how do we do this one? So this cone's radius is r, okay, and the mass is given as m. Okay, let's think of this like, let's say this angle is theta, okay, and this height of the cone, let's say, is capital H. This is obviously r. Okay, from this point we go a distance x, okay, and we take a small thickness dx. So this will form a disk like this, and this disk thickness is dx. Let's find the moment of inertia of this small element. Okay, so we know from the same result di. Okay, let me demarcate this, otherwise someone might get confused. Okay, so di, moment of inertia of this small disk, is half dm r square. Now r here is small r. Okay, now so let's write r square. Now how can we find r? Now see here, tan theta is r by h, capital R by h. It is also equal to small r by x. Okay, so r we can write as x tan theta. Okay, the volume of the cone, let's say V, is pi r square h by 3. So for this element's mass dm, will be total mass m divided by volume times volume of this mass, which is pi small r square times dx. So if I substitute, this becomes m by pi r square h by 3 pi small r square dx. So pi gets cancelled. So this turns out to be 3m r square dx divided by r square h. We can also write h as r tan theta. So this becomes 3m r square dx by r square into r tan theta. So r cube tan theta. Okay, so that is my dm. So now let's substitute all the values. So half dm is 3m small r square dx divided by r cube tan theta times r square. Now small r square is x square tan square theta. Or we can write, let's say 3 by 2 m by r cube, r to the power 4, right? So x to the power 4 tan to the power 4 theta divided by tan theta this should have been cot theta. This should have been cot theta. So r cube cot theta. This is cot theta. So this becomes 10 to the power 5 theta. So we can write 3 by 2 m by r cube x to the power 4 10 to the power 5 theta dx. Now if I integrate, all of this is a constant, so 3m 10 to the power 5 theta divided by 2r cube, these are all constant. We have integral x to the power 4 dx. Now what's the range of x? X is from 0 to h. 0 to h. Now this is 3m 10 to the power 5 theta divided by 2r cube. This is x to the power 5 by 5, so 1 by 5, and if I substitute the value of x, so h to the power 5. Okay. Now tan theta is r by h, so we can write r to the power 5 by h to the power 5. This is 1 by 5 h to the power 5. This and this gets cancelled. This 2 cancelled. So this becomes 3 by 10 mr square. So this is the moment of inertia of a cone about this axis. Okay. So that's our solution.